types of force and Newton's third law of motion, modelling and sketching force diagrams. Can you think of any different types of force that you've come across previously, perhaps in GCSE physics? You may have heard of these types of force. Weight, which is the effect of gravity acting on the mass of an object. Tension, which you might find when you pull something. Compression, which is sometimes also called thrust, which you might find when you squash or squeeze something. Friction, an example of which is air resistance, which is also called drag. You can feel the friction if you rub your hands together. There's a frictional force between your hands. The normal reaction force, or the normal contact force, it's a force experienced by an object when it is in contact with the surface. The surface pushes up on the object. The driving force, braking force, which is a force created by the effect of an engine in a car, for example. We're going to have a look at how to sketch force diagrams and how to model physical situations. If you're solving a problem involving forces, it is absolutely essential that you sketch a clear and labelled force diagram. You will not be able to solve force problems without one. Even if the problems look simple to start with, they will build up to much more complex scenarios. And in year 13, these scenarios involving forces will become even more complex. It will be impossible to solve these problems without a good diagram. Your diagram must show all the forces acting and their directions. Now, let's have a look at this concept of modelling. We use this to try and simplify a physical situation. For example, if an object has a particularly complex shape, it's very difficult to investigate how all the forces act on it, the directions in which they're acting, for example. So we simplify the situation and we treat the object as a single particle. This is one very simple example of a model that we use, and you'll find out more and more about this as you get further into the forces topic. So we're going to have a look at some simple scenarios. We're going to look at the modelling that's involved, and we're going to sketch force diagrams for each of these scenarios. Example 1, an object is placed on the ground. Let's have a look at the forces acting first of all. So here's our object, in blue here. Now, the forces acting, we have the weight, which acts downwards, vertically downwards. We also have the normal reaction force, or the normal contact force, which is the force of the ground pushing up on the object. The normal reaction force always acts perpendicular to the surface of contact. That's why it's called normal. Now, the modelling involved in this scenario, we are modelling the object as a particle. Now, this has a very specific meaning in mechanics as a modelling word. It refers to a single point object which has negligible dimensions, so we don't have to worry about its length, its width, its depth, or anything like that, and all of the object's mass is concentrated at this single point. And we usually model a lot of objects as particles. It simplifies the situation completely and allows us to do the calculations successfully. Now, this last example leads us neatly into Newton's third law of motion. We'll be looking at the first and second law a little bit later on. Now, this law states that when one object exerts a force on another object, there is always a reaction which is equal and opposite in direction to the acting force. In other words, for every action, there is an equal and opposite reaction. And the last example illustrates this really well. We can see that the weight of the object pushes down on the ground, and the ground exerts an equal and opposite force upwards on the object, which is our normal reaction force. Example 2. A tennis ball is hung on the end of a light, inextensible string. And there are some modelling words here, which we'll talk about in a minute. So the forces acting, the weight which acts at the centre of mass or centre of gravity of the object in a vertically downwards direction, and then there is a tension force in the string acting vertically upwards. The ball is modelled as a particle, and the string is modelled as being light. This means that it has what we call negligible mass. So we assume that this mass of the string is so small compared to the mass of the actual object that we can ignore the mass of the string. So we don't have to take the mass of the string into account when later on we do some calculations. We also model the string as being inextensible. Now this means it cannot stretch. Now the knock-on effect of this is that it means that the tension is constant throughout the string. So we don't have to worry about the string having different tension values in different parts of the string. Now, these models are not necessarily perfect, but they simplify the situation at this stage of our knowledge and understanding enough for us to be able to do the basic calculations. When you learn more and more about mechanics and more about forces, you can refine your model and you can make your model more complex so that your answers more accurately reflect what would happen in the real world. Example 3. I push a box along a rough table. Again, this is an important word, rough. Let's have a look at the forces acting on the box. So here's the box and here's its weight acting vertically downwards, which is balanced by a normal reaction force of the table pushing up on the box. Here's me pushing in one particular direction. I've chosen to push from left to right. I could have chosen to do that in the opposite direction, but I've just drawn my diagram in this way. And here's friction opposing the direction of motion. So friction always opposes the direction in which an object is actually moving or the direction in which it is attempting to move. I'm attempting to push that box from left to right, so friction is going to work against me and work from right to left. Friction always opposes the direction of motion or the intended direction of motion. It's really important that you remember this. Again, we're modelling the box as a particle. Now the table is modelled as being rough. This means that there is a frictional force acting on the object. Sometimes we model a surface as being smooth, and this means that we assume that the friction is so small that we can leave it out of our calculations, or we assume that there is no friction. In reality, in the real world, it is very, very difficult to find a surface that is truly friction-free. Ice would be a possible example, an ice rink perhaps, but even then there will be some level of friction. So in reality, this idea of a smooth surface, this would only really exist in our mechanics models. In the real world, we can get surfaces that are very close to being friction-free, but it would be very, very difficult to find a completely friction-free surface. Example 4, a car is driven along a road. So let's have a look at the force diagram again. Here's the car. Here's its weight. Here's the normal reaction force, vertically upwards, perpendicular to the surface of contact, the road. Now, the engine of the car will exert a driving force, taking it forwards. I've chosen to make the car drive from left to right. And of course, remember what we said, friction opposes this direction of motion, so friction will be in this direction. Now, the frictional force will be composed of friction between the tyres and the road, and also air resistance or drag if the car is travelling fast enough. Sometimes an object may not be moving fast enough for air resistance to have any kind of effect, in which case we sometimes ignore the effect of air resistance, or we say that air resistance is negligible. If an object travels very fast, then for air resistance will start having an effect. So the faster you travel, the more likely you are to be affected by drag or air resistance. Again, looking at the modelling words, the car is modelled as a particle and the road is modelled as being rough. You may question the validity of a car, which is a really large and complex object, as being modelled as a particle, but again, this might be the best we can do at the moment, and it's good enough for a simple model. We have to acknowledge that models are not perfect. They may not give us completely accurate answers, but they will give us a good rough estimation. And from there, you can work on refining your model, looking at which aspects of it were perhaps not perfect or not good enough, and then making adjustments to your model to see how that affects your calculations. Example 5. I hold a pencil in the air and I push on both ends of the pencil. So you can see here I have a pushing force like that and a pushing force like that. The pencil is described as being in compression, which is sometimes also called thrust. So compression forces are sometimes referred to as thrust forces. Think of the idea of squeezing something in. If instead I pull on both ends of the pencil like this, the pencil is described as being in tension. Now, some interesting modelling assumptions here. The pencil is modelled as being a rod, which has a very specific meaning in maths again that you need to learn. It is an object with one dimension that is small in comparison to another. For example, it's got a definite length in this case, but a comparatively small width. So we only consider the length of the pencil, the length of the rod. We don't worry about its width. Now, a rod is usually considered to be what we call rigid, which again has a very specific definition in mechanics. This means that it does not bend or buckle.